Hello, and thank you for joining me. You're here with Data Science Teacher Brandyn, and we're here for simple random forest project, our ML machine learning projects today. Level 1, we're going to keep it as easy as possible and go through how to build a random forest model today. Okay, so today we're going to be predicting banknote authentication, whether it's real or fake bill. Okay, so we have some notes. Not a computer vision problem, just a regular spreadsheet type of data set. Okay, so we're going to start off with importing our libraries here. So we're going to import pandas as PD, import matplotlib.pyplot as plt, import numpy as np, import seaborn as sns, and import warnings. Now, this is a good idea. Honestly, you don't have to do warnings, but you'll find that even, especially with machine learning, there's lots of warning messages, things that could be changing in the future. They're not really super important on a day-to-day basis, though, and so they get a little bit boring to see every time. So I usually turn them off just because it gets a little bit, and I'm having a hard time typing as I'm talking. So we're going warnings, import warnings, warnings.simple filter. So for that, we're just going to pass simple filter the string ignore, and it's going to ignore the filters. It's really super easy to turn them off, and it's kind of easy. We're not going to use numpy a lot today, but it's such a good idea to import it. I don't know if we ended up using it today, but it's a good idea just to import it, because if you don't, you always end up needing it, sort of thing. This is kind of just because we might need it, sort of thing today. It's just good to start with those ones. Good to get in the habit of importing those 4 libraries. Okay, including matplotlib. Even if you think you're only going to use seaborn, you might want to change a title or something like that and import matplotlib. It's usually something you'll need. Okay, so we're going to load up the data. We have left over the code, and thanks to John, I forgot to mention that as well, John David, give him a thanks on his LinkedIn and his Facebook for helping me design the whole entire workbook today. A really, really good job. It was great working with him. And so thank you again, John, for helping me out with this one. And I look forward to your next project. Okay? And you can check out the data set here on Kaggle right here if you want to get to it. If you go to that website, the Kaggle website, and you download your own data set, you can upload it here on Google Colab. You can upload it right to this workbook from your computer. Okay? Or what you can do is you can mount it from your Google Drive. You run this, you give it security access, and then you will be able to select, you go to your folder, and you'll see these 3 lines. You go copy path, and you'll be able to put this right in the pd.read.csv. Or if you want to do it the easy way, I have this in my GitHub reservoir, so you can just download the data set right from there, and you don't have to make any changes. So the one thing about this data set, it had no column titles, which I felt kind of annoying. I wish they had put column titles. There was in the data dictionary, though, which is what I copied this from, which is the website to go to the data set. If you find that, so I put names, and I manually had to put these in, but it's good just to start with the names in there, so I don't have to make the change. So names, and I'm going to list the names when I'm importing the data with read CSV, and then we'll just look at the head of the data set. And again, I'm importing it from my GitHub. Okay? So you can see here we have 4 numeric columns and 1 class, which is what we're going to predict, 0s and 1s. Okay? So we have to look at the head of your data set and the tail of my data set to get, if there's kind of some obvious errors, they're usually at the top or the bottom, and just anything you need to be conscious of. Okay, another good idea is to understand how many rows and columns we have. Just get a good sense. Make sure that we have 1,372 and 5 columns. Okay, it's good just to write down these observations. They're pretty basic, and this might be super obvious, but as you're preparing these reports for other people, you have to understand that some people might not have any idea even what this shape is, right? You've been doing this for a while, you know what this is. But you have to think that someone might be reading this. Is a great thing about Jupyter Notebooks is people can read these without knowing code. So really, it's the expectation really that you're going to write these observations down, and just like you're out in the wild, you're watching some animals, you're writing down exactly what you see. I see this. I see this. So you don't have to sell. You don't have to change anything. Just exactly what you're seeing. You're writing down your observations, and then you can then use these observations as to-do lists for pre-processing in your machine learning, or insights that you're gaining that you want to share and stuff like that. So it's good just to collect these as you go. Kind of, you'll need to write them down anyways, and it's good just to review these observations. It's easier to review these observations often than it is to go back and look at plots or look at some analysis that you've done. So just a good habit. I know it's really simple, but it's good practice. Even when I'm doing it for myself, well, maybe for myself, I might not write down rows and rows and columns, but I honestly write down most observations for myself as well, because it ends up helping you and saving you time later. So we're doing this one. The next one we'll do is .info, and this is really important to check the data type. So we have floats and integers. If we saw one of these that we expected to be numeric columns to be an object, we would know we have some things to fix and some stuff to look through. So it's always good to check the data type. If you don't, it usually comes back to bite you in the bum later on. So it's good to check that. We wanted to get a quick look at the distributions, a quick glance at each of the distributions. We go df.describe, and it gives us a 5-point distribution. So the min, the max, 25th, 50th, and 75th percentile. And we also get the average here. The 50th is the median, and we get the standard deviation too as well. So you can start to get some insights about this data set. We know instantly that if we have zeros and ones and less than half is, or more than half is 0, so then we know that more than half is class 1. Okay, so there's a little bit of an imbalance. We're getting insights. We can see as well, we have a little bit of a tail and kurtosis. It looks like tilts off to the right a little bit. Same with skewness as well. So you have some outliers that we need to be conscious of. Okay. So df.columns next. So you're looking at an attribute. I'm not putting parentheses here. The parentheses tell Python that I'm calling the function that use this function. This is an attribute. So just say, well, I actually show this as well. So if we have .describe and we don't put the parentheses, you see we don't get an error. This is actually something you need to do sometimes in Python, but this is referencing this function. Like, hey, Python, here's a function. Don't use it, but here it is. So if I want to use the function, I have to put parentheses after it that says, hey, Python, here's a function, and use the function. And even if I'm not going to give it anything in the parentheses, I still need to use them just to say, Python, here, use this function. Okay, so that's why columns is an attribute, just asking for some details. I'm not giving it any information. That's why I'm not giving it parentheses, because it's not a function. I just want some information, some detail, like your hair color. I want to know something. I don't want to tell you to do something. I just want to know something. Okay, so here we're going to go is null dot sum parentheses dot sum parentheses as well. And this will give us a count of the null values in our data set. We're going to do duplicates. So, and then we're also going to check then how many rows are duplicated. We see here we got 24 duplicated rows. That's kind of important to be conscious of. You find that sometimes, I wouldn't say it's the most common. We only had 24 out of 34, but really that's going to mean that our model doesn't train really correctly on new data. We're replicating some of the rows, so it's going to learn those situations more. If those are all exactly the same 24, it could be just one row repeated 24 times. Again, that would be make our model a little bit biased. So we're just going to be conscious of that. So what we're going to do is we're going to go drop underscore duplicates. There we go. And when we have 24 less rows. Okay. So getting into our EDA section, we're going to do a little bit of plotting, or we're going to change some of the styles. I get bored of the standard style, so we're going to set Seaborn style to be dark grid, and we're going to use PLT style.use BMH. And this changes the color palette that they're using and kind of makes the grid, or I guess the axis object, the square, a little bit of a different color. I think it looks quite nice. It's something different. Got to change it up or you get kind of bored after a while. Okay. So here what we're going to do, in the first one we're going to do, look at the class, look at the imbalance of our class. So we're going to do a count plot. Okay. SNS.count plot, class, and then data equals df. In the next line, we're going to go for p in x patches. Patches is essentially taking out each one of this square, the objects inside of my plot, and iterating through them. So when we iterate through it, we're going to a note based on the height and the position of each one of the grids. So we use the height to know what the number is on top of it and put the number on top of it. It is a little bit more advanced, but just, again, it's really quite simple because we're just ax.patches is a list of each of the objects, and then we're going to iterate through that and put it on. It is a little bit tedious, and so we're not going to do it today, but it is good to be aware of how we would do this higher level editing into each object inside of a grid. So we can go down to that. It does get a little bit tedious to do that, but it's pretty easy to do this and add the count to the bars. Okay. So in the next one, we'll do df.hibs. So we're going to do a pandas plot here, And then in the next one, we're going to do tight underscore layout. Now, what tight layout does is it essentially just, when we're putting a grid together, it rebalances, doesn't just make everything tight, it rebalances everything so it has a nice kind of spacing, positions and stuff. And this happens when you start putting many plots together. It's really usually a good idea to do this. And then the last thing we're going to do is figure, so that we can make a fig size, 29 by 17, just a little bit bigger than what we would have space for. All right, you got to spell tight correctly. So T-I-G-H-T, layout. I thought that was a word. I didn't notice there wasn't a T right away. But again, you just go slow. I'm used to making errors in front of students now. But you just go slow and you understand, well, why did I make that error? And you kind of read the message and really, oh, it's something to do with tight layout. And so it has to be here. Okay? So there's no magic happening. You just kind of really got to go slow when you get an error. Take a deep breath, look at the error, and try and find out what happened. Because it's going to be somewhere up the chain. You'll be able to follow it and really just kind of keep going to where the root of the error is. Okay? So the next one we'll do is we're going to do a dis plot. Okay? Now this is a higher level Seaborn function plotting, although it looks here just like a histogram. It does a couple extra interesting things. And one of the reasons that we want to use Seaborn in the first place, all Seaborn plots have this hue argument that allows us to change the coloring of the distributions based on this. In this situation, usually what you'd want to do with machine learning is look at the change in the distributions based on the class, the target of what you're trying to predict. Okay? And this really, we can see here that the variance has a very big difference in our target. So that probably means this will be a good feature to use in predicting our model. Okay? And the next one, we're going to do displot. We're going to go data equals df, x equals skewness, and hue equals class. Plot that, and then plt.title, skewness distribution. Okay, so you see this one does not make as much difference, although we do see that there is still quite a large difference. It's not quite substantial as the other one. This would still likely be a very good feature. Okay, and this in the last one right here, what we're going to do, so you see here, I'm using the hue argument to change class, and we're putting them on the same plot. The cool thing about this is it's a figure level plot, so we can actually create many plots at once. And this is different than the hist argument, the histogram plot. This allows us to do a little bit more. Okay, and so here what we'll do is we'll do col to be column, or column is the class. And now each, instead of being on top of each other, different colors, we now have them separated by the class. And we can break this up a little bit further. We can even take this step. Let's say we don't want them side by side. We want them on top of each other. We can go row equals class. So now they're going to be two plots. This also looked a little bit off when I was doing it. It just kind of seemed it was too big. It was really quite long and stuff. So if I want to change the size, I can go height equals 3, and this will be for every individual one. And then if I go aspect is, if it's 3 high, it's going to go 1.5 times wide, and that makes sense usually for a distribution plot to go a little bit wider than tall, because we really don't need to see how height is. We need to kind of understand the distribution, the width of the distribution. Okay. And so there we go. Getting into the bivariate analysis. Okay, so here what we're going to do is we're going to do subplots, and this is another way that we can get the figure size. So we're going to set this in the background, and then our SNS plot is going to go on top of this. Okay? So here we're going to do our font size. We're going to say heat map, and then inside this we're going to pass core. Okay, so df.core. A note equals true. Really good to have a note equals true so we see the little numbers, vmax, vmin, just what these are, and then square. And then yellow, green, blue is our color palette, which I think it truly looks a lot nicer than the standard one, because Seaborn has amazing colors. I would say the heat map is the only one that I personally don't like the standard colors. Maybe you do, but I think it's usually one of the ones that I change the colors with CMap to do a continuous color palette. Okay. The next thing we're going to do a pair plot and understand the bivariate relationship. We're going to say hue equals to the class as well. And we can see that we got pretty good when this is done running. We'll see that it's probably going to be a very easy prediction state, and we can see by how much the hue is separated, or how much separation it shows really in almost every feature by the hue. It means we have a lot of different options to use for predictions. I would say entropy by kurtosiness actually doesn't show this. The only one that really doesn't have such a distinct, where there's really a good separation between the two classes. But I think we'll find it quite easy to make predictions today, just based on this graph. There you go. So looking at the next one. So what we'll do, we'll get into our modeling section. Dun, 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 random forest. Okay. So I usually like to just go df.columns when I start this and make a list of this. And I'm going to copy and paste these things into my features. And make a list of my features. I'm going to put the class, the target in the class. Make sure you don't duplicate these. So make features, a list of features, and make target a list of, well, in this case, just one target. Okay. So then what I'll do in the next one, I'm going to go x equals df and then features on the inside. And a large X is machine learning. We usually do a large X. It's good just to follow what everyone else does. So it's easier to understand other people's code when you're looking to borrow it from the internet. Okay. And so here we're going to do this. And so we're essentially going to create X is equal to df features. So we're selecting out these 4 columns, becomes our X, and a Y becomes our target. Okay. We're going to import train test sets. So from sklearn.model_selection, import train _test _split. Do that. And what we're going to do here, we're going to do our train test split. So we're going to do X train, X test. Okay. Y train, Y test. So train test split, X test, Y train, Y test. Okay, then we're going to give these X and Y that we just created up above, train test size, this split, random state. I usually set it to 42. It's kind of kind of an inside joke in Python in general. They use random state 42 a lot. Look up the Hitchhiker's Guide to the Galaxy if you want to know what that inside joke was about. Okay, so I'm doing the train test it. The reason I want to set the random state is because I wrote notes about lots of stuff I saw, and I want to make sure the things happen the same. So I'm able to the notes are consistent. So if you're ever going to share your project with people and you're going to write stuff about it, it's good to set your random state. It's good to make sure that you're seeing the same thing over and over again so that really the split is the rows are randomly sampled in the same way. So in the next one, we're going to do the scaling. So after we've done the split, we need to make sure that we are going to do standardizing. And we do this afterwards because we're going to use the mean and the standard deviation learned from the train set to standardize then the train and then the test. So we're only going to learn from the training set, which is machine learning. We can't be learning from the test set. It's kind of cheating. And so we want to learn from the train and then transform the train and the test all new data based on the same parameters that we learned. So just, you will notice you get a slightly better score if you don't do it, if you do this before. Because it's kind of cheating. You're using information, you're learning from your data, although it's not necessarily exactly directly machine learning, you're learning some statistics, some information from that. And so that stuff might not exist in your training set. So we need to be careful about that. And that's why we're doing this afterwards. So I think there's a couple other ones, but I think of standardization, something like principal components, PCA. I think of those as your machine learning, really your modeling data. It's what your model does to the data as it takes the data in. Right? So after we do our splits. Okay, there's some pre-processing that you want to do before, and there's some that you want to do afterwards. Okay, so we're going to do a logistic regression data. It's good usually to do more than one model to get a sense of how my model is predicting. We wanted to see really how much better random forest did than logistic regression. But as I said, it was going to be an easy data set today, so maybe logistic regression is enough for our use case. And this is why it's usually good to try different models. Usually random forest can do quite a bit better than logistic regression, so it's always good to try. I like to try a simple model always as a baseline to really see what I'm trying to beat. Okay? And what we're going to do here, after we do this, we're going to go fit. So we import our model, we initialize our model. I'm setting a few of the different hyperparameters in my model, and I'm assigning it to LR. LR.fit. So I'm training my model, I'm learning all the details about how to perform calculations, the mathematics that happens inside. So this is where my model does the learning. In the next one, I'm going to go sklearn.metrics, import plot confusion matrix. So this is a really handy function that will just plot the confusion matrix right away. So I'll go plot underscore confusion matrix. I'm going to give it the model, give it X train and Y train. I'll plot this. And again, we've already trained our model. This is a trained model that we're giving to this plot. And we'll see here, it'll just do the predictions for us inside this function and then do, I think this is on a heat map, a Seaborn heat map. And the next one we'll do PLT. We'll plot the confusion matrix for we're giving it the model, the train model, the X test, and the Y test. And we're going to go PLT.title. plot right here, and we get a nice little handy, very, very nice handy little function. The next ones, we're going to go LR. We're going to try and get our accuracies first. So by default, in a classification problem, when we go LR.score or model.score, we get our accuracy score. So this one here, and we can see on our train accuracy, we got 99%, which is pretty good. So we're collecting the scores though. We're getting our train and our test scores, and we'll put them all down in the summary right at the bottom. So we'll be able to see them all next to each other. Okay. So here what we're going to do as well, we're going to sklearn.metrics, import classification report, and then classification report. Goes right here. And we have to print this out, putting this inside a print function so we see everything. And just note as well here, you give it yTrain, yPredict. And what I'm doing, I didn't save yPredict here. So what I'm going to do is I'm just putting lr.predict and xtrain inside this, and that's going to give me yPredict, yPred, but I'm not going to save it anyway. So this is going to be here for the time and just putting it in there. It's not too long to do this. So just a different way to do that. Okay? If I never needed to use it for anything else, why would I save it? Right? So, and then looking at it for the test score, we see we got very good scores, a little bit less than perfect on the test, which is good. You'd expect a little bit worse than you would on. Okay? So here, got an error, which is not a surprise. So we're going to go from sklearn.ensemble, import RandomForestClassifier, and we're going to go RandomForestClassifier. With that, we'll send that to RF. I find the defaults really good. I thought it was good just to start with the defaults, and they worked really well. These are some of the things that I was planning on trying, but I ended up not really needing to do a lot of the hyperparameter tuning or playing around a lot with the hyperparameters, but I put some of the common ones here so you can play around with them. Okay, so just as we did below, we're going to initialize a model to RF, and then we're going to fit our model, and where the learning happens, .fit. And if it's a big data set, this could take a really long time. Here, it's quite small, so we're not going to spend too much time. And then just like we did above, we're going to go plot underscore confusion underscore matrix. Perfect. Okay, we get that. We're getting a perfect score on our training data here. So let's put in our test data. So we'll go plot confusion matrix and then plt.title in the second line. And there we go. We see we make a couple of mistakes, but we're doing really good predictions overall, I would say. So then in the next one, we're going to get the accuracy scores, just like we did up above. So we're going to go x underscore train, comma, y underscore train. And then in the next one, we're going to go, x tests, x underscore test, and then y underscore test to get our train and test scores. Okay. And look at that, we got 100% on our training set. I wonder what we got on the test. So let's go finish this. As I said, we're doing the predictions here on the train and the test just to get our y. So let's predict here, and then we compare our y predictions against our true values, our training data, and our predictions in the next one. So on these two, and we can see you're doing really, really well on really both of these. So let's plot the tree a little bit. Let's look at one of the decision trees inside of our random forest. It's quite a bit of work to see the whole random forest, but we can start inspecting all of this. So to get this first, we're going to import the plot tree function. So we're going to sklearn.tree, import plot tree. We're going to create a bigger figure size, and we're going to go plot underscore tree equals, and then we're going to pass that rf.stmatrix. And then you're going to do underscore. This is an attribute, and just in sklearn, for whatever reason, they want you to do an underscore after an attribute, just to signify you're not doing parentheses, I guess. But here what we're going to do there. Okay, so here what we're going to do feature names, and then we're going to give it the column name. We're going to give it the first 4 column names because the last column name is the target. So let's put the target in here. We'll go class name as well here. Okay. And this should be class name. Sorry, apologies. Class names. Okay. And then we're going to fill them so they're colored. We'll show the impurity and we'll show the number it's random to. So, and we can inspect this. Oh, and we got to make sure we spell figure correct. Lots of spelling mistakes today. I'm surprised actually I didn't make more. I usually make more when I'm just by myself, but trying to perform well for an audience. Okay, so here we have our plot, and the way to read this is For true, it goes to the right. So we see here that the variance is less than a number. So it's not less than goes to the left. It's when this is true, it goes to the right. And when it's false, it goes to the left, and so on and so on. You can follow this down. So many insights that you can gain from this. This forest is made up of 100 trees, and they're all going to be a little bit different. So you got to be a little bit careful about how much insight you extract from these decision trees. But they are quite interesting to explore in a lot of detail. And it's really quite pretty, the decision trees you get out of this. So, okay, so let's go into that. Let's look at the overall scores to comparison. So I usually put this into a data frame. So we'll go pd.data frame. Okay, and look at our models, and we'll put this into we're putting a dictionary into a data frame. So you see this in the curly brackets here. And in the first position of curly brackets, the key is the model and a list of the scores. And then the second item is the key is score and a list of the scores. And so you just notice that we're keeping the same position, 4 and 4, so they line up. And always got to spell things correctly. That E and the R button are really close when you're going fast. Okay, and so you can see here, we got very similar scores. You see 99.1, 99.3. Logistic regression did better. We can't for sure say it did better, truthfully, because it might just be a statistical difference. If you were to hypothesis test, it's too small of a difference to actually say one is actually better than the other, because it might not be in practice, right? So, but a good thing to take away is that logistic regression can do quite well, can do as good as RandomForest. This data set was very easy, I would say. So take this with a grain of sand, but it's always good to try a simple model with a complex model. Really what you'll find is your simple model will maybe get your logistic regression, you're going to get a 0.7, and then that will be your baseline of what you're trying to improve upon, and really you're trying to beat that by a substantial margin when you get to a powerful model like RandomForest. Okay? Again, we're really focusing on our test scores here, because that's really our closest comparison to what we would see in practice on new data. Really what we're looking for is the difference between the train and the test. To have confidence in our test, we would expect to see the train and the test to be very similar. If the train was higher or lower, it would draw into a lot of questions into our test set. Because the risk, you'll hear overfitting a lot, and overfitting isn't just about getting bad predictions. You can actually get crazy predictions. So you might slightly reduce your scores, but sometimes you might get, you've mapped the randomness, you've learned all the randomness, you really overfit to it, and when that randomness is balanced differently, you're going to get crazy predictions. And so that's really the risk. That's why we're so careful about overfitting, is because it's not just bad, it's really crazy. And so it's good to really take this in thought. We don't see any overfitting here. We see a little bit of a change, but that's kind of standard, 1 point less. And really perfect is quite good. I would be concerned with perfect, but because I got so close to it on my test, I know that it was really just the fact that it was such an easy data set to do today. Okay. Well, thank you very much for your time today, and I will see you all next time.